My name is Richard Zimmerman. Welcome to my living room, and thanks for watching my video presentation on a measure of lexical dispersion I have been working on, dubbed word growth dispersion. Lexical dispersion describes how evenly or unevenly a word is spread out in a corpus. The concept is useful to adjust frequencies, for example, for vocabulary lists, to test for the constancy of a cultural concept, to see if a word has become used more regularly over time, for instance, in grammaticalization studies. I will first show how word growth dispersion is calculated, then I will say a few words about its interpretability, and finally I will apply the measure to natural language corpora. Okay, so here's how you calculate word growth dispersion. The measure is based on word growth curves. A word growth curve, here WG, is a set of ordered pairs of the position of a particular word type in a corpus and its index from its first to nth occurrence. For example, the word growth curve for the word book in the 1 million word Brown corpus would be constructed by recording the first instance of the word in position 23,916, the second instance in position 27,631, and so on, until eventually the final 195th instance is encountered in position 990,125. Overall, book is mentioned relatively steadily throughout the corpus. However, some corpus parts show more dense sequences of the word, for instance before token 200,000 and around token 500,000. Other passages involve a more moderate increase in the word count, for example between tokens 200 to 400,000 and 700 to 900,000. In addition, there are several bursts of extremely rapid succession of the item at around token 100,000 and just before the end. And there's also a long lag where the word is hardly attested at all, roughly between tokens 500,000 and 700,000. Word growth curves thus offer an intuitive way to assess the evenness of a word's distribution, and it therefore seems promising to use them as the basis for a dispersion measure. First, the distances between every word occurrence are calculated. The distance delta for a word is simply its position minus its immediately prior position starting from the second occurrence. For instance, here's the word growth curve for a word with 5 occurrences in a 50-word corpus. The distance is calculated by taking the position for the second occurrence and subtracting the position of the first occurrence, then by taking the third occurrence and subtracting the second occurrence, and so on. An additional distance will be added called delta 1, which comprises the remainder of the corpus. It corresponds to the distance between the beginning of the corpus and the first instance of the word, plus the last instance of the word and the end of the corpus. As a consequence, the sum of all distances will correspond to the corpus size, and so an alternative way of calculating delta 1 is to subtract the sum of all other distances from the corpus size. The distances are then simply the set of all distances, delta 1 to delta n. The next step in the calculation of word growth dispersion involves determining the uniform distance. The uniform distance is the expected distance if a word is perfectly regularly dispersed. It is the ratio between the number of n total tokens in the corpus over n occurrences of the target word. For example, if there are 5 occurrences of a word in a 50-word corpus, then the uniform distance will be 50 over 5 equals 10. If the distance between every occurrence is exactly 10, then this word would be dispersed absolutely uniformly in the corpus. Then you can calculate divergences of the actual distances from the uniform dispersion of a word, called deviation of distances. This is calculated simply as the difference between the actual distances and the uniform distance. This calculation is illustrated here for the 195 instances of book in the Brown corpus. The second column shows the position of every occurrence, and the third column the distances. The universal distance in this case turns out to be 5,139 tokens. Actual second and third distances are 3,715 tokens and 7,539 tokens. So the deviation of distances is minus 1,424 and 2,400 respectively. The former interval is shorter, the second longer than what would be expected under perfectly even dispersion. Now it is possible to calculate a measure of spread of the deviations. This can be done with the mean absolute deviation, or MAD. The MAD is simply the average of the absolute deviations of distances. So you sum up all the absolute deviations and divide them by the number of distances. To illustrate, the MAD of book in brown is 6,081 tokens, which means that the distances are on average 6,081 tokens off, so either longer or shorter than perfectly regular intervals. The measure should be normalized. This step requires the calculation of the worst possible MAD given a particular word frequency and corpus size. The least regular distribution of a word is obtained by arranging all occurrences into a single sequence of immediately adjacent hits. A worst-case distribution of this kind is illustrated here for 20 occurrences in a 10,000-word corpus. All 20 occurrences appear in a row, and that leaves one single really long distance for the rest. So there will be n-1 short distances. Here there are 20 minus 1, 19 short distances, and the deviation of each of these distances is 1 minus the universal distance n over m. And there's one really long distance of size n minus n plus 1, so here 10,000 words minus 20 occurrences plus 1, which is 9,881 tokens. You need to add this plus 1 so that the sum of all distances add up to the corpus size. Then you simply divide the sum of the absolute deviations of these distances by n. For instance, the worst possible MAD of the word book in brown turns out to be 10,224 tokens. In other words, it is impossible for the distances of a word of that frequency in brown to diverge, on average, by more than that number from its uniform distribution. Incidentally, there's also an easier calculation of the worst MAD. Since half the probability mass resides in the shorter distances and the other half in the single long distance, you can also divide the respective deviations by half the sample size. At any rate, the unadjusted word growth dispersion measure, DWG, is calculated by dividing the actual MAD by the worst possible MAD. The result is a dimensionless quantity that is comparable across different words and corpus sizes, and also conveniently constrains the values to the interval 0 to 1. Word growth dispersion of 0 is achieved when a word is perfectly well dispersed, with all of its distances matching the uniform distance, so that its divergences are 0, and 0 divided by the worst possible MAD is 0. Word growth dispersion of 1 results when a word follows the most uneven dispersion possible, and so the worst MAD divided by the worst MAD is 1. The unadjusted word growth dispersion for the word book in brown is the MAD of its deviation of distances, namely 6,081 tokens, divided by its worst possible MAD of 10,224 tokens, which gives an unadjusted DWG value of 0.595. Finally, the measure must be adjusted for the relative frequency of the word, that is to say, for the percentage of the corpus that is made up of the target word. To see why this is important, consider a case with a very high saturation. Here's the distribution of a word with 6 occurrences of a word in an 8-word corpus. So 75% of the corpus, 6 out of 8 tokens, are actually just the same word. In this case, the worst possible distribution becomes very close to the uniform distribution, and therefore the dispersion measure must be corrected for the level of saturation. I developed a geometric solution for this problem. The angle between the y-axis and the worst distribution, alpha, is always 45 degrees. In contrast, the angle between the y-axis and the uniform distribution, beta, ranges somewhere between more than 45 degrees and less than 90 degrees. So the unadjusted DWG measure can be corrected by division with 2 times the ratio between alpha and beta. If the uniform distribution is very far away from the worst distribution, then the angle beta will be close to 90 degrees. 45 degrees divided by 90 degrees is 0.5 times 2 is 1. So the DWG value will basically be the same as the unadjusted DWG value divided by 1. However, if the uniform distribution is very close to the worst possible distribution, then the angle beta will be close to 45 degrees. 45 degrees divided by 45 degrees is 1 times 2 is 2, and so the DWG value will basically be cut in half and tend towards 0.5. Now, typically, there is a small number of word occurrences in a very large corpus, say 100 occurrences in a 1 million word corpus. If this is the case, beta will be very, very close to 90 degrees, and so the unadjusted DWG and the adjusted DWG will basically be the same. For instance, the unadjusted DWG value for book in brown is 0.595, and its adjusted DWG value is also 0.595. The adjustment really only matters for high-frequency words. And even then, it's not terribly important because words in natural language corpora don't usually make up more than maybe 10% of the corpus. For example, the most common word in brown is the definite article the, and it accounts for between 6 and 7% of that corpus. The unadjusted dispersion measure for that word is 0.369. Its adjusted value is just slightly lower at 0.353. So in real-life settings, the adjustment is really more cosmetic and not essential. Anyway, this is how word growth dispersion is calculated. I would now like to talk about what the output of the calculations I just presented actually mean. There are several ways to make sense of a word growth dispersion value, but I will only offer one, namely an interpretation in terms of random dispersion. So, I randomly distributed word occurrences in the corpus and measured the resulting DWG value. I repeated the process over and over again to get an average. And I conducted this experiment for different relative frequencies and for different absolute frequencies of the word. For example, here you can see the experiment running for a random distribution of a word with 10 occurrences in a corpus with 10 million words. This gives a relative frequency of 1 per million words, and in total I collected 250 samples for every setting. Here's the result for a randomly dispersed word with 10 occurrences in a 10 million word corpus. The DWG values turn out to be normally distributed, as shown by a number of tests for normality. I take this to be a desirable feature of word growth dispersion. The average DWG value of a randomly dispersed word is about 0.37. This can serve as a convenient benchmark for a well-dispersed word. Importantly, these findings hold for different relative frequencies and for different absolute frequencies. That's shown in this figure here, which summarizes the findings for all parameter settings in this experiment. The value of 0.37 is constant for different relative frequencies on the x-axis, normalized to per million words, and for different absolute frequencies, as shown by the dots for different corpus sizes. To summarize, the DWG value for randomly dispersed words are normally distributed with a mean of about 0.37. This measure is scale invariant. It holds for all relative frequencies and for all absolute frequencies, and the finding offers an important benchmark. It suggests that well-dispersed words should have a dispersion value of, say, less than 0.4. It is now time to look at word growth dispersion in action, as it is applied to actual natural language corpora. I calculated the DWG values for all words in a number of corpora. I will present 3 examples here. The first corpus is brown, representative of written American English of the 1960s. Contains 1 million words in 15 different genre files. The second corpus is beige, a corpus of spoken British English in an academic setting with a size of 1.6 million words in 160 transcripts. And lastly, I created a custom-made Spanish corpus with 1 million words that includes 10 books of different genres. This figure shows the distribution of DWG in the 3 corpora. The overall distribution of DWG is quite similar in all corpora, which is an encouraging result. DWG in natural language is not normally distributed, but right-skewed. That means that many more words are badly dispersed than well-dispersed. There are virtually no words with near-perfect distribution in natural language. Token distances between word occurrences are not anywhere near identical in actual texts, and so a DWG value of less than roughly 0.3 just does not arise naturally. In contrast, there can be words that are very badly dispersed with a DWG value of greater than 0.9. For example, here is the word growth curve for the word binomial in brown. The corpus includes one text in which the word binomial is frequently mentioned in rapid succession, and as a consequence, the dispersion of this word actually approaches the worst possible dispersion with a DWG value of 0.998. These kinds of examples are very common in Bayes, where a technical term may appear very frequently in one kind of academic lecture, but never anywhere else. Hence, dispersion reveals that Brown is a more general language corpus, whereas Bayes is a more specialized corpus. It is possible to calculate the quintiles of the DWGs, where each of the 5 groups contains the same percentage of observations. This is indicated with the red lines in the histograms here. Based on these quintiles, I propose a 5-scale interpretation of word growth dispersion values as they apply to real-life empirical situations. A DWG value of less than 0.45 indicates a very well-dispersed word. If the value is between 0.45 and 0.525, the word can still be regarded as relatively evenly distributed. On average, any given word will occur with a DWG value between 0.525 and 0.6. An unevenly dispersed word has a value between 0.6 and 0.7, and if DWG is larger than 0.7, then the word should be assessed as very uneven. I will now look at the relationship between frequency and DWG. This graph shows the data from the Brown corpus. The x-axis shows frequency on a log scale, and the y-axis shows DWG. As you can see, the correlation between dispersion and frequency is fairly low. In my opinion, this is another desirable characteristic of DWG because it shows that the measure successfully maps dispersion and frequency onto 2 distinct dimensions. However, there is some predictable connection between a word's dispersion and its frequency. The most common words also happen to be very well dispersed. These are function words such as the, and, of. These items are indistinguishable from random dispersion. There are also some words that are fairly common but also highly genre-specific. These are, of course, pronouns, especially gendered pronouns like he and she. For instance, the word I can only occur in first-person narrative texts, like diaries or direct speech, but it is often completely absent from many other genres. In between, we find, for example, auxiliaries like would or may. Well-dispersed, less common words are those that are difficult to classify as either functional or lexical, such as well, make, probably. Words that are extremely badly dispersed tend to be technical terms like thyroid, names like Winston, or year numbers. And in between, there is an enormous number of words whose dispersion values are not easily predictable. For instance, cold, rule, contrast, no, rate. There are thousands and thousands of words that show great variation in their spread. And it is predominantly for these words that a dispersion measure is interesting and useful. These findings are not new. Rather, they replicate very closely previous results. Therefore, these findings validate DWG to some degree as an instrument that does in fact measure lexical dispersion. It is also possible to test whether DWG is valid by correlating it directly with other dispersion measures. Here, I show the relation between DWG and another dispersion measure called DP. The correlation between DP and DWG will be higher for distinct frequency classes because DP has a much higher correlation with frequency than does DWG. Nevertheless, there is a high overall correlation between the two measures of about 0.78, which further confirms that DWG is in fact valid as a measure of lexical dispersion. Alright, so this concludes my presentation. I hope that word growth dispersion will become a useful addition to the set of dispersion measures that corpus linguists have been developing. I think it's an advantage that the measure can be calculated on a single corpus part. It also has some other nice properties, such as at least some straightforward ways of interpreting the value, scale invariance, and low correlation with frequency. Of course, further experiments are needed to validate the measure, and in particular to estimate how much DWG varies as corpus parts are rearranged. Lexical dispersion may seem a bit like an exotic niche topic to work on at first, but I think it's actually very important because dispersion measures are needed for some foundational questions in corpus linguistics. Dispersion may be one of the best handles on deep theoretical questions, the problem of how words are actually generated and distributed, the difference between general and specialized corpora, productivity, and perhaps most importantly, representativeness. Okay, I would like to thank the organizers of ICAME for moving the conference online, as well as everybody who has been watching this video. So thanks, please stay healthy, and I'm looking forward to meeting you in person at the next conference.